decades, supersonic flight has been synonymous with the loud, disruptive boom that accompanies breaking the sound barrier. But the X-59 QueSST is set to change that narrative. A product of NASA's collaboration with Lockheed Martin, this experimental aircraft is designed to achieve supersonic speeds without the familiar sonic boom. With a sleek design and innovative technologies, the X-59 promises to open up the possibility of quieter, faster travel, making the dream of commercial supersonic flight a reality. Here's a look at how this revolutionary aircraft could transform aviation as we know it. Supersonic aircraft, capable of flying faster than the speed of sound, Mach 1, represent a leap in aviation, driving technological innovation in military, research, and commercial sectors. The Tupolev Tu-144, which first flew in 1968, was the first supersonic airliner, but its commercial career was short-lived. In contrast, the Concorde, which entered service in 1976, succeeded in revolutionizing air travel by drastically cutting transatlantic flight times. Although its high operating costs, environmental concerns, and sonic boom limitations led to its retirement in 2003. The race to achieve supersonic flight began with military aircraft, with fighter jets evolving to meet the growing need for speed and agility. The Bell X-1's historic flight in 1947, where Chuck Yeager broke the sound barrier, set the stage for future developments in supersonic aviation. Throughout the 1950s, several experimental aircraft exceeded Mach 1, with Jacqueline Cochran becoming the first woman to break the sound barrier in 1953. The 1960s brought supersonic airliners, including the Tu-144 and the Concorde, but the economic challenges of operating such aircraft soon became clear. The sonic boom and high maintenance costs proved burdensome, and the Concorde's 2000 crash further diminished public confidence in supersonic commercial aviation. Aerodynamic drag is a significant challenge at supersonic speeds, demanding innovative wing designs. The swing wing design, which adjusts wing angles at different speeds, and the delta wing used by the Concorde helped mitigate this issue. Supersonic aircraft also face extreme heat due to friction, requiring the use of advanced materials like titanium and heat-resistant alloys to withstand these temperatures. For propulsion, early supersonic aircraft used turbojets and rockets, but afterburners, which burn extra fuel in the exhaust, became the preferred technology. The SR-71 Blackbird, powered by Pratt & Whitney J58 engines, exceeded Mach 3 thanks to this innovation. Breaking the sound barrier generates shock waves, creating the disruptive sonic boom that remains a challenge for widespread adoption in civilian aviation. Today, supersonic flight is paving the way for hypersonic aircraft, which aim to exceed Mach 5, pushing the boundaries of aerospace engineering and shaping the future of flight. Despite setbacks, the legacy of supersonic aviation continues to influence the development of next-generation aircraft. As the noise of the past begins to fade, a new kind of supersonic flight is taking shape. One where the disruptive sonic boom may finally be a thing of history. A sonic boom is the thunderous sound unleashed when an object pierces the sound barrier, sending shock waves rippling through the atmosphere. These waves, bursting with immense sound energy, can echo like an explosion or the crack of thunder. Even on a smaller scale, a supersonic bullet or the crack of a bullwhip vividly demonstrates this remarkable phenomenon. When supersonic aircraft shatter the sound barrier, their booms resonate across the landscape, startling communities and sometimes causing a minor structural damage. This disruption has led to a ban on routine supersonic flights over land. While erasing sonic booms entirely isn't possible, groundbreaking research suggests that reshaping an aircraft's design could soften these booms, hinting at a future where overland supersonic travel might take flight once more. Contrary to common belief, a sonic boom isn't a one-time blast, as an object crosses Mach 1 around 741 miles per hour at sea level. Instead, it's a continuous ripple effect, trailing the object as it speeds through the sky. Observers hear the boom only when the shock wave's cone sweeps past them, creating a fleeting but powerful auditory experience. Much like a boat displacing water, an aircraft pushes air aside, generating pressure waves that compress and merge as its speed increases. When it reaches supersonic velocity, these waves form a shockwave cone. The pressure spikes at the aircraft's nose, plunges into negative pressure at the tail, and then stabilizes once the aircraft passes, a sequence known as an N wave. This pressure cycle creates two distinct booms, the first as the pressure rises, and the second as it normalizes. If the aircraft maneuvers mid-flight, the shock waves shift, forming a U wave with a different sonic signature. As long as the aircraft remains supersonic, this boom-producing cone persists, casting a narrow boom carpet onto the ground below. The boom's reach and intensity depend on altitude. At higher altitudes, the boom softens and its footprint widens. However, lower altitudes amplify the shock waves, intensifying the boom. The strength of a sonic boom can range widely, from a mild 50 Pascal to an ear-pounding 500 Pascal. The most powerful recorded boom, generated by an F-4 Phantom flying just 100 feet above the ground, reached a staggering 7,000 Pascal. While such extremes can shatter windows, most booms are far less intense, leaving buildings unscathed at pressures under 530 Pascal. Aircraft size and shape play a critical role in boom intensity. Larger aircraft spread the boom's energy over a wider area, often softening its impact. Secondary shock waves, caused by features like wing edges or engine inlets, can add to the boom's ferocity, especially at lower altitudes where drag increases. Above 40,000 feet, sonic booms tend to fade, offering a quieter ride. Yet the challenge remains. Supersonic flight at these heights can be fuel-intensive due to heightened drag. Striking a balance between altitude, efficiency, and boom suppression is the key to unlocking the future of supersonic travel over land. But it's not all smooth sailing. As the first tests unfold, the X-59 will face some surprising challenges that could put its quiet supersonic promise to the test. The dream of quiet supersonic travel inches closer to reality. But will it be enough to overcome the persistent challenges of controlling shock waves? The theory of minimizing sonic booms was once speculative, but it became a reality with DARPA's Quiet Supersonic Platform project. At the heart of this effort was the Shaped Sonic Boom Demonstration SSBD, an experiment that modified an F-5 Freedom fighter to gather vital data on sonic boom reduction. The F-5E's nose was extended and a fairing added, creating a streamlined aircraft for conducting 21 test flights over 2 years. With the help of a chase plane, engineers captured over 1,300 recordings, including some from within the shockwave itself. The results showed a significant reduction in boom intensity by about a third, offering a glimpse of how quieter supersonic flight might look. Building on this success, NASA partnered with Gulfstream Aerospace in 2006 to test the Quiet Spike, a telescoping boom on an F-15B designed to minimize shock waves during supersonic flight. After over 50 test flights and data analysis from a second aircraft, it became clear that boom mitigation was improving. Yet, eliminating sonic booms entirely proved elusive, as some designs, like the Bussmann biplane, highlighted the inevitable shock waves generated by supersonic lift. In 2018, NASA took a leap forward by awarding Lockheed Martin a $247.5 million contract to develop the low-boom flight demonstrator, later named the X-59. This aircraft is designed to make sonic booms as faint as a car door closing, an innovation that could pave the way for overland supersonic travel. The X-59, developed by Lockheed Martin's Skunk Works division, is at the forefront of this sonic boom evolution. As part of NASA's Low Boom Flight Demonstrator, LBFD project, it aims to silence the disruptive boom that has hindered supersonic travel for decades. With its sleek design and specially contoured nose, the X-59 reshapes shock waves to create a soft thud instead of a traditional boom. This breakthrough could make supersonic travel over populated areas a reality once again. Flight testing is crucial to the X-59's success, with NASA gathering data on public perceptions of its reduced sonic boom. These results could influence future regulations, potentially paving the way for supersonic flights over land. If the X-59 meets its milestones, it will redefine air travel, balancing speed with environmental and community concerns. The aircraft's journey to this point has been rigorous, with extensive safety reviews ensuring the X-59 meets NASA's high standards. These evaluations have set the stage for the aircraft's next phase, real-world flight testing. As Lockheed Martin and NASA prepare for the aircraft's first flight, they are also preparing for potential regulatory changes that would allow supersonic flights based on sound levels rather than speed alone. The X-59's design is based on the lessons of previous experiments, such as the 2003 F-5E test flights. By reducing the boom's intensity to about 75 decibels, roughly equivalent to a car door closing, the X-59 has the potential to transform the future of air travel, proving that supersonic flight can coexist with quiet skies. With the technology evolving, it's not just about flying faster, it's about changing the very rules of the sky. The next phase is on the horizon, and it's more than just a flight test. The Lockheed Martin X-59 QueSST, conceptualized in 2018, represents NASA's bold vision for revolutionizing supersonic flight. Fueled by a $248 million grant, Lockheed Martin's Skunk Works team transformed years of research, wind tunnel tests, and design refinements into a cutting-edge aircraft, unveiled in January 2024. At 99.7 feet long and 29.5 feet wide, the X-59's sleek, needle-nosed form is a testament to aeronautical innovation. Its cockpit, uniquely positioned midway along the fuselage, highlights its futuristic aesthetic and streamlined purpose. Engineered for speeds of Mach 1.4, approximately 925 miles per hour, the X-59 blends bespoke innovation with repurposed components. Landing gear from an F-16, the canopy and ejection seat of a T-38, and engine elements from a U-2 spy plane are seamlessly integrated. Its top-mounted engine plays a pivotal role in maintaining a smooth underside, preventing shock waves from converging into a disruptive sonic boom. Instead, these waves dissipate, reducing noise levels to an unprecedented degree. The X-59's revolutionary design also replaces traditional forward-facing windows with an external vision system, XVS. High-resolution cameras feed real-time images to a 4K cockpit display, enabling the pilot to navigate efficiently without direct visual contact. This approach not only supports the aircraft's aerodynamic efficiency, but also exemplifies its forward-thinking engineering. As the X-59 progresses toward flight testing, NASA plans to conduct acoustic evaluations over select cities. Residents, briefed in advance, will provide feedback on the muted sonic boom, aiming to validate that noise levels meet regulatory thresholds for overland supersonic travel. This data is expected to influence global aviation standards, encouraging regulators to permit commercial supersonic flights that minimize ground-level disturbances. The X-59's advancements resonate across the aviation industry. Startups like Spike Aerospace and Exosonic are drawing inspiration from NASA's research. Spike is working to redirect sonic waves upward, while Exosonic develops a 70-seat aircraft designed to reduce sonic booms further. These innovations signal a broader industry shift toward quieter and more sustainable supersonic travel. However, challenges remain. Supersonic jets face scrutiny for their environmental impact, with some models potentially consuming 3 times the fuel of subsonic airliners. To address these concerns, NASA and industry leaders are exploring alternative fuels like hydrogen and electric propulsion. Boom, another supersonic pioneer, is developing the 80-seat Overture to run entirely on sustainable aviation fuel, SAF. While optimism abounds, securing investment and proving commercial viability are critical hurdles. The X-59 could be the key to unlocking a future where supersonic jets are no longer bound by the sonic boom's roar. What comes next could reshape global air travel. Now, Lockheed Martin's Skunk Works, in partnership with NASA, has reached a major milestone in the X-59 QueSST program by completing the aircraft's first engine run tests. This achievement marks the transition to fully autonomous operation, where the X-59 powers itself using its internal systems for the first time. These tests are a crucial step toward taxi trials and the highly anticipated maiden flight of this groundbreaking experimental jet. In late 2024, engineers conducted a comprehensive evaluation during the tests, verifying the performance of critical systems, such as the engine inlet and nozzle, structural and system integration, and engine control algorithms. Previously reliant on external power for hydraulic, electrical, and pneumatic systems, the X-59 now operates entirely independently. The engine run tests successfully demonstrated the precision management of the F414 GE100 engine through the vehicle management system and onboard engine computer. This phase also confirmed the functionality of the fuel system, vibration controls, and temperature regulation. Pat LeBeau, the X-59 program manager at Skunk Works, shared his enthusiasm for the achievement, noting that it was an emotional high to see and hear another innovative, boundary-pushing Skunk Works X-plane come to life. The team has done an incredible job and remained focused on the path forward to a safe and successful first flight. The live testing of the F414 engine, which generates 22,000 pounds of thrust, is vital for verifying the X-59's ability to achieve its ambitious goals. Initial engine tests began cautiously, with engineers spinning the engine at low speeds without ignition to check for leaks and ensure system communication. This was followed by low-power runs to identify anomalies and assess interactions with onboard systems. As the testing progresses, the engine will be pushed to higher power levels and subjected to rapid throttle changes to simulate flight conditions. This rigorous process ensures the X-59 is prepared for its upcoming taxi trials which will involve low and high-speed maneuvers, setting the stage for its inaugural flight. Beyond its experimental role, the X-59 serves as a technological pioneer, demonstrating the feasibility of supersonic flight without disruptive sonic booms. Though the X-59 itself will not enter production, its design and technological advances are intended to provide a foundation for the next generation of supersonic airliners. By freely sharing insights from the program, NASA hopes to inspire the aviation industry to overcome noise and sustainability challenges, paving the way for quieter, faster, and more efficient air travel. The X-59 QueSST is no longer just a concept, it's a reality taking to the skies, and its test flights are already challenging the boundaries of aviation. As it continues to undergo rigorous testing, this groundbreaking aircraft is poised to redefine the future of supersonic travel, offering a quieter, faster, and more sustainable alternative to the noisy past of high-speed flight. The X-59 could soon pave the way for commercial aircraft that break the sound barrier without breaking the silence, setting the stage for a new era in aviation.